Okay, in this video we'll talk about unitary transformations, which are linear transformations that describe a rotation of a vector space, complex vector space. Okay, so let's remember what we talked about in the last video. There we described a rotation of a two-dimensional real space. And that had a very nice description to it. It was described by this 2 by 2 matrix, which we call R of theta in terms of sines and cosines. And then we also said, let's look at a rotation through minus theta. And that was given by actually the transpose of this matrix, R theta. And so since rotating through minus theta undoes the effect of rotating through theta, we have R theta times R theta transpose is the identity. Right? So this is very good intuition for what happens with unitary transformations in general. Okay, so let's describe general unitary transformations. So let's say we are working in a k-dimensional complex vector space. So now our linear transformation, the rotation matrix, is going to be a k by k matrix. So let's say the linear transformation we have is a k by k matrix with complex entries. So now we'll say that U is a unitary transformation or a rotation of that space if when we look at U conjugate transpose. By this we mean every complex number that occurs in this matrix, and you take the complex conjugate and then take the transpose of this matrix. If U dagger, U conjugate transpose times U equal to U times U conjugate transpose is the identity. Right? So U is unitary if and only if this condition is satisfied. So let's look at this in detail. So let's assume we are working with a 2 by 2 matrix. So U is of the form A, B, C, D. Remember, A, B, C, D are complex numbers. So what does U dagger look like? So U dagger, you're going to take the complex conjugates of these entries. So you'll replace A by A dagger, A conjugate, D by D conjugate, and then you take the transpose of the matrix, meaning the off-diagonal entries are transposed to the other side. You flip them. So C goes down here, but it's not C, but C conjugate, and B goes up here, but it's B conjugate. Okay, so now this condition U dagger times U is the identity. What's it telling us? Well, it tells us that A bar, B bar, C bar, D bar times A, B, C, D is the identity, meaning 1, 1, 0, 0, identity matrix. Okay? All right, so again, let's try to interpret this. So first, let's try to understand what's this matrix U represent, right? So it's telling us what happens to the space. So what's U do to the zero vector, right? To the zero state. What's the zero state? This is A, B, C, D. The zero state is this vector. And so what do you get? You get AB. Actually, it picks out the first column of U, which is A0 plus B1. Similarly, U times 1, it picks out the second column of U. Okay. Now, what does this relationship tell us about where 0 and 1 get mapped to? Well, can we say something about the relationship between A0 plus B1 and C0 plus D1? Well, we can look at the inner product. What's the inner product? Well, it would be given by, for example, this times that, right? This times that is the inner product between this vector AB and CD. But that's exactly that entry. So we know the inner product between these two vectors is 0. So they're orthogonal to each other. What's the length of these vectors? Well, that's given by the length of this vector AB is given by the inner product between this with itself, right? Of the inner product of AB with itself, which is the product of this times that. And that's this entry. So that tells us that the length of this vector is 1. And similarly, the length of this vector is 1. So what this tells us is that what a unitary transformation does is, or at least for 2 by 2 unitary, what it does is it maps the 0 vector and the 1 vector both to unit vectors, which are also orthogonal to each other, which is what we expect from a rotation of the space. In fact, we can see this more generally for a general k by k unitary matrix. So what do we know about this? Well, we know that the 0 state gets mapped to this first column, the 1 state gets mapped to the second column, the state k minus 1 gets mapped to the kth column. And now let's see what does u dagger times u equal to identity tell us. So here's u dagger. So we take these columns and we flip them on the side, and then we take the complex conjugates. This is u dagger. That's u with these k columns. And this is, the product is 1, 1. It's the identity. So it's 1 on the diagonals and 0 everywhere else. So now, what do we want to know? We want to know what's the length of one of these vectors. Well, the length of a vector you can get by taking its inner product with itself. So you look at this vector, and then you want to look at this, you want to multiply it by the corresponding row vector, but with the complex conjugate. So you get the same, if it's the second column, you want to take the second row. And then you get the inner product, but the inner product is 1 because this was a diagonal matrix. It was an identity matrix. So that tells you that the length of each of the columns is 1. What if you want to know, okay, what's the relationship between the ith and the jth column? Well, you look at the inner product between them, meaning you look at the product between the ith row here and jth column. And what you get, you look at the ijth entry. If I is not equal to j, we know that all of these entries are 0, which means that the inner product is 0. And so these columns are orthogonal to each other. Right? So the states 0 through k minus 1 get mapped to orthogonal states, which are also normalized. Now, here's another thing we can say about a unitary transformation. We can say that U preserves inner products. What do we mean by that? So let's say that we start with 2 different states, phi and psi. And what we do is we apply u to each one. So we look at u phi and u psi. The claim is that the inner product between phi and psi is the same as the inner product between u phi and u psi. Okay, so how do we see this? Well, the inner product between these two is just given by, okay, what's the inner product between these two? Well, this is a ket, right? This is u times psi. It's just another vector, right? Because u is a matrix times psi, and that's another vector. So this is another ket. But u times phi is also a ket. How do you get a bra out of it? So this is a column vector, but what you want to do is you want to take its conjugate transpose to get a row vector. So you want to take the conjugate transpose of this. So you should take the conjugate transpose of this. And you remember the rules for taking the transpose of a matrix. So if you want to take the conjugate, you just take the conjugate of all the entries and you get the conjugate. But to take the transpose, you would take the transpose of the transpose of AB is the transpose of B times the transpose of A. So you take the transpose in the opposite order. So you would get, right, you'd get something like this, which is what? Well, this is actually bra phi times U dagger. Okay, so what's the inner product between these two? Well, you take bra this times ket that, which is bra phi U dagger, and then this is already a ket, so you get U times psi. But U dagger times U is the identity, so these two are equal. So this tells you that U always preserves inner products. So it always preserves angles between vectors.